So we will work on section 12.5. Consists of two parts. First one, equations of lines. And then the second part, equations of planes. First one, on lines. Suppose in the three-dimensional coordinate planes, I think I should say coordinate space, we have a line going through a point, call that point P naught, which is X naught, Y naught, C naught. Just call that P naught for now. And then this line going through is parallel to, this line is parallel to vector R1. Oh, sorry. So this line here is parallel to vector R1. Okay, call this line L here. Line L contains point P naught. That's X naught, Y naught, C naught, and is parallel to R1. Now, the factor equation of L, line L, is given by RT, so that's a factor function actually, RT equals to R naught plus T R1. You know what? Instead of using R, let me change the notation. Instead of R1, let me use V, vector V. Okay, now we call this factor V here direction factor. We call that direction factor. And R naught is the position factor of that coordinate. Okay, so the factor equation of that line L is given by the position factor. The position factor is position factor here. Okay, and then this is R naught, and this is V here. And the direction factor is the V. I hope the notation R naught, R0 makes sense, because when you set your T equals to 0, when you set your T equals to 0 in that factor functions, you will see just the position factor function. Okay, the position factor P naught. Now, if I break this factor equation up, so suppose my RT basically XT yt ct, right? This is equal to x naught, y naught, z naught, that's the R0, plus t times v1, v2, v3, which is the direction factor. So this is our R naught, the position factor of one of the coordinate on that line, and this is phi factor phi, the direction factor. Okay, now I use t here just to signify that the coordinate x, y, z depends on your t that we use. Of course, t here can be any real numbers. From that factor equation, then we come up with parametric equation. The parametric equation of line L is written, you learn parametric equation in calculus 2, right? Supposedly. So notice that I basically rewrite that factor equation in components. So x component will be x0 plus t phi1. And the y component will be y0 plus t phi2. And the c component is z0, z0 plus t phi3. Notice that the RT equals to the position factor R0 plus T times direction factor V. Okay, this guy, this guy, this guy. Okay, that's the parametric equation. So in some sense, of course, then if you know the factor equation, you know the parametric equation. If you know the parametric equation, you know the factor equation. Okay? Now, the third way of writing equation of a line is by solving for t. And we will get what they call symmetric equation. The symmetric equation of L is given by this. Yeah, solve for t. If you solve for t here, you will get x minus x naught over phi1. That's equals to t, right? And so on and so forth. You will end up with x minus x naught over phi1 equals to y minus y naught over phi2 equals to z minus z naught over phi3. I'm sorry. I think I think I used a wrong letter here. Not symmetric, but symmetric equation. Okay. Now each equation, each way of writing it has its own good thing. But one of the weakness of symmetric equation is what happens if one of your v is actually equal to 0. Okay, then we cannot use symmetric equation, or the symmetric equation needs to have some extra description. Okay, let's do one example. Suppose, for example, call this example 1 then. A line contains coordinate 2, -3, 4 at the direction of 1, 4, -2. Oh, when you do your quiz and your tests, I need you to be aware that if you write it using parentheses, that's a coordinate. For you to write a factor, you need to use this wedge notation here. But Thomas, you know what I mean? No, I don't. I have to understand you from what you write. Okay? Understanding you different from what you write is the true definition of being biased. Okay? If you want me to understand what you mean, then you are the one responsible to write it properly. Okay? Now, if you don't write it properly, then of course I have to, I may not understand it the same way. Okay? A coordinate is a coordinate. It is on coordinate plane or coordinate space. But a factor, on the other hand, is coordinate free. Okay, it can move around. It just cares about the magnitude and the direction. Okay, so please distinguish when you write a coordinate and when you write a factor. Okay, so suppose I want to write the factor equation. The factor equation is RT. Notice I use that factor notation for that R equals to factor position 2, -3, 4. Notice I don't use parentheses, but I use wedge here for position factor plus T times 1 for -2, which we can put together as T plus 2, comma, 4T minus 3, comma, -2T plus 4. So at the same time we learn this first example, we also notice that how we write that in factor notation, the factor function notation, the constant of each component tells us one of the coordinate of that line. Just set when t equals to 0, then you get that this 2, -3, 4, right? Okay. Now then, the coefficients of the t's tells us the direction factors, how it is parallel to. Okay, so the direction factors it parallel to here is 1, 4, -2. Okay. Not only you need to know how to get the equation, you also need to know when you have an equation, what you actually have. Okay, now second, how about the parametric equation? I myself, if you ask me, Thomas, which type of equation you prefer? I prefer either factor equation or symmetric equation, preferably factor equation. Of these three, the one I like the most is factor equation. Parametric equation takes more space because I have to write it this way. Of course, you can write the t terms first, then the constant. Okay, now the symmetric equation. The symmetric equation, basically when you solve for t. So if I solve for t, I will get x minus 2 over 1. Sometimes I don't write that over 1. Y plus 3 over 4. And then z minus 4 over -2. Okay? Note. What happened then, instead of having the direction factor, if you tell me two different points on a space. So suppose I have P1 and P2 on a space. How do I find the equation of the line passing through these 2 points here? Well, you can use either one of the coordinate to get your position factor. Okay, and then you create a factor from P1 to P2. Then that is your direction factor. Okay, so we can say in this case RT, our factor equation of the line, will be R naught plus T phi, but the phi is actually coming from R1 minus R naught, if this is our R1. And this is our origin. Okay, playing here and there, you will see that we sometimes write this as R naught, 1 minus R naught of, what am I doing? 1 minus T, 1 minus T of R naught plus T times R1. But of course, you still need to simplify that if you get the numbers, okay? But abstractly, the abstraction, that's what it looks like. Okay, now notice that R1 minus R0, that's basically the direction factor. Okay, now I will discuss a bit about how this how these lines interact with another line. For example, let's make a note first. Note. Line 1 is parallel to line 2 if and only if, first, the direction factors are parallel, and so not only that they are parallel, direction factors are parallel, at the same time, they don't have intersection. In other words, line 1 intersect line 2 at empty space, empty set. Now, if we go back to two-dimensional coordinate system, we say two lines are parallel if the slope are the same, right? M1 and M2 are equal, right? But what happens if they are exactly identical lines? And you will see M1 and M2 are equal, but they are not parallel. In fact, they are identical. Okay, the word parallel means they don't intersect. In fact, they intersect nowhere. Okay, so when we show that two lines are parallel, we need to show that two lines are parallel. You need to show two things, that two factors, the direction factors are parallel. They may be opposite direction, that's okay, as long as they're parallel. And then they don't have common point. Okay, another way, I think what another things that I need to emphasize is what happens if you only show that the direction factors are parallel and you don't show that they don't have common points. Well, you may end up with parallel lines, I mean identical lines. Okay, maybe I'll write it as a side note here. I'll write it as a side note. Line 1 equals to line 2. Maybe they may look like they may have different equations in the outlook, okay, but you will see that two lines are the same lines if the direction factors are parallel and the intersection is not empty. In fact, you will see if the intersection is not empty, then they actually intersect everywhere. Okay, Now, we will work on this first case first. Okay, suppose, for example, I think this is example number 2. For example, we have line 1 given by R1t. We call that t parameter. 2, -3, 4 plus t times 1, 3, -2. And then another line, line 2, that's R2 S not t. I cannot use the same parameter.
Professor.
Yes,
On the previous note, what's the upside down U represent?
This one here?
Yeah.
Intersection.
Say that again?
Intersection.
Okay.
Intersection. Like if when you learn set the interval notation maybe in the past, like if you have this interval between 2 to 4 intersect with let's say -5 to 3. 2 to 4 means between 2 up to 4, including 4, not including 2. And then -5 to 3, it's -5 up to 3. It's this one here. What happened? Now, the intersection of these two intervals represent the interval or coordinates or points that they have in common. Now, in this case, that will be interval 2, 3.
Okay.
Does it make sense? So intersection, basically what they have in common.
Okay. Thank you.
Sure. Now, then line 2, let's go back to the questions. Line 2, let's say it contains 0, -9, 6 plus s times -2, -6, 4. Okay, now you may wonder, Thomas, why don't we use t's for both of them? Well, the reason is the t for the first guy, the first line, the time for the first line may not be the same time for the second line. Okay, so instead of like using the same t as if they have the same time, as if both of them moving from the same point in time, we should not assume the same way. Okay. By the way, let me say this first. You very likely driving, right? Very likely you're driving. Okay. So this RT here actually tell us the trajectory of you driving. Let's say I drive from this point to that point. Okay. And who knows you actually drive from this point to that point. Okay. So we do intersect here, right? Now the thing is, simply because my trajectory and your trajectory intersect doesn't mean we have accident. That's why we have the traffic light, right? Traffic lights makes your intersecting trajectories not, even though your trajectory is intersecting, but you don't have accident. Why? Because when I was here, for example, you may be here. By the time I already get away from that intersection, already here, you are then here. You see what I mean? Okay. When I get to that intersection, you are still stopping. Once I already get away from that intersection, then you start moving. So even though my trajectory intersect with your trajectory, it doesn't mean we have accident. Okay, so to have an accident, you need to work very hard for that though. Not only that, your trajectories and that person's trajectories has to intersect, you need to intersect at the same time. So every time you have accident later on, you will remember Thomas, right? Because the way to explain the accident is not only your trajectory intersects, your time also happen to be at the same time there at the same point. Don't underestimate this comment though, because one of the things that you may do sometime later on. I have this in my previous class. I give them some project. Suppose somebody is actually Iran or North Korea send a missile coming to the United States, and you need to intersect that with your Scud or a Patriot, another missile. Okay, so one thing you need to make sure is like your trajectory, our trajectory, intersect with that missile's trajectory. That's one. Second, it has to intersect at a point where you reach that point at the same time. What you don't want to happen is like the missile's not there yet, but you already pass it. That's kind of like a waste of missile, right? A waste of intersector. Does it make sense for you? Okay, so of course we don't want to have accident, but when we are in defense and you have a Patriot, the purpose of that Patriot is to intersect incoming missiles. And if possible, you intersect that incoming missiles far away from our homeland. Okay, what you don't want to happen is like you intersect that missiles, like, and then right below that missile is actually California. And that missile happens to be a nuclear warhead. Okay, now even though the explosion is far from the ground, okay, but the dust of radiation will fall down. In fact, the further away it is from the ground, the more spread the dust of the radiation. Okay, now I hope you start seeing why you learn Calculus 3. One of the big demand that a lot of people don't go to is going to defense. Okay, our country recently is talking too much about something else, and we don't really see how other people actually, trust me, even Indonesia, the country where I come from, my people in my country is actually laughing at America recently. It's like with the current situation we have here, you name it. Okay, they look at us and say, hey, you know what? We don't need to attack America. It will actually crumble on its own weight. Okay. Oh, let me go back to this example then. How do we show that two factors are parallel? Two factors are parallel if the cross product give us factor 0. But we have seen in the past, I think I can go back to our notes from the past here. I did show you that two factors are parallel, right? Means one factor is multiple of the other, right? Okay. Two factors are parallel if the cross product equals to 0, okay, which basically means one factor is multiple of another factor. Okay, we will use that. So instead of doing the cross product, which is harder to operate, we will instead show that phi1 is equal to a multiple of phi2, a non-zero scalar multiple of phi2. Okay, now going back to our example 2, notice that line 1 is parallel to this factor. Let's call that phi1, which is 1, 3, negative 2, and line 2 is parallel to phi2, which is negative 2, 6, negative 6, 4. Okay, note that phi1 is parallel to phi2 because phi1 is negative 1/2 of phi2. Okay, the ratio is negative 1/2 for all three components, not only two of them, not only one of them. So once you can tell that one factor is multiple of another factor, then these two factors are parallel. Therefore, so line 1 is parallel to line 2. Okay, so we already answered the first part that those two factors are parallel. Oh, I'm sorry, I cannot conclude that yet. I'm sorry, I cannot conclude this yet. All I have right now is two factors are parallel, but I still need to check that those two lines has no common point. Okay, line 1 intersect line 2 is empty set. Proof. Why is that? Well, let's see if they have an intersection. Suppose to contradiction. Suppose they have L1 intersect L2 is not an empty set. Okay, then the position factor of line 2, one of the coordinate on line 2, which is 0, -9, 6, must be reachable. Think of it this way. If they are parallel but they have one common point, they must be common point everywhere, right? Which implies I can use line 1, to reach any points in line 2. One of them is 0, -9, 6. Okay, so 0, -9, 6 equals to 2, -6, 4 plus t times 1, 3, -2, 4 some t. There is a t such that when I use that t, I will get this thing. Okay, suppose to contradiction, they have a common point. Then all points must be common. And if they have all common points, then I can randomly choose a point from line 2 and find the t from line 1 to reach that coordinate. Okay, now if I try to solve this, notice that we come up with this equation. The x component equals to t plus 2. The y component equals to 3t minus 3. And then the c component will be -2t plus 4. Now, from the first equation, t is -2. From the second equation, we also get t equals to -2. Unfortunately, from the last equation, we get t equals to 1. Okay. In other words, when the x is reachable with t equals to -2, at the same time t equals to -2, the c component is not reachable. In other words, this is a contradiction to contradict t equals to -2. Now, it is possible for you to be parallel that you must have the same t. Okay, here we see that they have different t. I think it should be -1 instead of +1. Okay, so line 1 intersect line 2 is an empty set, and by argument 1 and argument 2, I'm referring to this guy and this guy here, line 1 is parallel to line 2. Okay, next, note line 1 is and line 2 are skewed. Line 1 and line 2 are skewed if first the factors are not parallel, and at the same time, they have no common point. They don't intersect. Okay, Thomas, what I know is in 2 dimensions, once 2 lines are not parallel, they must intersect. That's true. In 2 dimensions, in 2D, if line 1 is not parallel to line 2, then the intersection is not empty. They must intersect somewhere. Okay? But because we have higher dimension right now, it is possible that you have skewed lines. Now, let me try to depict to you what is a skewed line. Imagine if you have parallelopipe. Parallelopipe, again, is a 3-dimensional figure whose sides are all parallelograms. Now, we may have skewed lines if the lines are on parallel planes. Okay, so like this one, that one, and this one here. You see? So this line 1 here and line 2 here, they are not parallel. Okay, they are not parallel. And at the same time, they don't have intersecting points. Why? How could that happen? Well, it happens because both of them are on 2 different planes that happens to be parallel. If those 2 planes are parallel, then they don't intersect, right? So any ingredients in plane 1 has nothing in common with any ingredient in plane 2. Okay, so what do we know about 2 skewed lines? Well, 2 lines are skewed if first they are not parallel and at the same time they don't have common points. When we try to see that geometrically in space, that can only happen if these 2 lines here are on 2 different planes that are parallel. Okay, now the thing is, I actually cannot make any reference to any planes in 3 dimension because we have not learned anything about planes, right? But at least you have seen parallelopipe. You know what it looks like. And I use that as a tool to show you what skewed lines look like. Okay, now then, you know what? Let me not erasing that. Now, suppose we now have an example. I think this is example 3. Show that these 2 lines are skewed. So we have line 1 given by R1T equals to 1, -2, 4 plus T times 1, 3, -1. And line 2 R2S. Notice my parameter. I use T and S. Don't make them the same. 0, 3, -3 plus S time 2, 1, 4. Okay, now solution. I think I need to write the question. Show that L1 and L2 are skewed. And for example 2, I forgot to write the question also. Show that L1 is parallel to L2. The first thing we need to work on is to look at the factors parallel to each line. So line 1 parallel to phi1, which is 1, 3, -1. and line 2 parallel to phi2, which is 2, 1, 4. Okay, first one, phi1 is not parallel to phi2 because phi1 is not equal to scalar multiple of phi2 for any k. Take a look. 1, 3, negative 1 equals to k times 2, 1, 4. If you have such k, then your k will be 1/2, right? From your x component point of view. However, when you see the y component, the k is supposed to be 3. And when you look at the c component, the k is supposed to be negative 1/4. Okay, but there's no uniform k that applies to all 3 components such that you get that 1, 3, negative 1. Okay, there's no such k. That means these 2 lines at least not parallel. Okay, but if 2 lines are not parallel, it is possible they intersect. So that's actually a note to say. Note, when line 1 and line 2 are not parallel, there are 2 possibilities. Line 1 and line 2 are skewed. That is when they don't have common point. The intersection is empty set. Okay, for line 1 intersect line 2 at one point. In fact, you can try in 3-dimensional space. If 2 lines are not parallel and they intersect, they must intersect at only one point. Okay. So if the intersection not empty, maybe I write it in more detailed here. If the intersection is not empty, then the intersection must be a point in space. Okay, using the argument I told you earlier about those 2 missiles, right? That's the point of intersection. Now, going back to that question, after I show that those 2 lines are not parallel by showing the direction vectors are not parallel, I need to show that line 1 intersect line 2 is an empty set. Because actually, I think a better way to write it is by doing the following. Step 1, claim. And then you say prove because. Step 2, you claim. And why? Proof, you say suppose is not empty. Okay, then there is a common point, a point common to L1 and L2, which also means there is a T and an S such that there's a T and an S such that R1T equals to R2S. That's the idea, right? Okay, now let's put it into practice. We set up the equation. So the equation for R1, the X component, we have 1 plus T. I wonder, can you see it? Yeah, here, like this. I think it's better this way. Oh, you know what? Let me write it next to here. So you see the X component, 1 plus T for R1 equals to 2S for R2 X component. For the Y component, in R1, we have negative 2 plus 3T equals to S plus 3. And then the Z component, we have 4 minus T equals to (4S minus 3). Now, let's see, how do we solve this? What happened here is we have 3 equations for 2 variables, right? So we just need 2 equations to solve 2 variables. So we can use any 2 of this equation here to solve for S and T. And then, so once you get the T and S, you check that using the third equation, do they match? If they match, then you have a common point. If not, then you have contradiction. Okay, let's execute it. What I'm about to do right now is basically algebra, something you learn in Algebra 1, Algebra 2, the latest is pre-calculus. Okay, so let's solve that. Let's call this equation 1, equation 2, and equation 3. From equation 1, we get T equals to 2S minus 1. Plug that into equation 2, negative 2 plus 3T. No, I changed my T, huh? Negative 2 plus 3 times T equals to S plus 3. And then I will solve for S here. Okay, 6S minus 3 minus 5 equals to S plus 3. So 5S equals to 8. S equals to 8 over 5. And the T is 2S minus 1. 16 minus 16 over 5 minus 1 is 11 over 5. Now, like what I said earlier, check against 3. Four minus T, oops, sorry. 4 minus T, is it equal to 4S minus 3? That's 9 over 5. Is it equals to, this is 32 over 5 minus 15 over 5. No, it's not, huh? 9 over 15 not equal to 17 over 5. Okay, so you see, if they intersect, there must be a T and S that satisfy this equation. Now, the thing is, we find the T and S from the first, second equation, but it is not consistent when we apply that to equation 3. In other words, there's no T and S that can solve all 3 equations at once. Okay? So, since there is no such T and S, then L1 intersect L2 at empty set, and by argument 1 that those 2 factors are not parallel, and argument 2 that they don't have common points, line 1 and line 2 are skewed. Okay? Now, let me tell you more. Things that I will do in my supplemental videos later on. If we have 2 skewed lines, which means they are on two different parallel planes, right? So plane 1 and plane 2 here are parallel. Then the next question is, what is the distance between them, between those 2 lines? But when we say the distance between 2 lines, you may wonder, Thomas, if I randomly pick a point here and randomly pick a point there, is this what we call the distance between 2 lines? The answer is no. That's the distance between 2 points that you chose. Okay, but the distance between 2 items always defined as the closest distance. So we need to find a point on line 1 and a point on plane 2, on line 1 and line 2, that gives us the shortest distance. Okay, that gives us the shortest distance. Now, that is something we will do later on after we learn more about planes. And given the time I have, I don't think I will be able to do it during a lecture. So I will do it on the supplemental video. Okay, I will suggest you some homework to work on. You do those first, okay, and then take a look on my supplemental videos. Okay, that's how you learn though. Okay, that's how you learn. You're supposed to think about those yourself. But if you don't want to think too much, at least you'll watch my supplemental videos and then start thinking, what if I ask similar questions in your test? Okay. By the way, after we are done with this 12.5, and once I'm done with the lecture, the supplemental videos for 12.4, 12.5, I plan to give you one very big quiz, basically a homework that you need to turn in. Basically, what I do is I give you 4 points in space. So in 3-dimensional space, let's say the first 3 points on this plane here, on plane 1, and point P, Q, R, S. Point S, let's say, is not on the plane. So so these 3 are on the plane, but point S is not. Then from there I have a lot of questions. Let's say, for example, if I give you the coordinates for all of these coordinates, then can you find, for example, equation of line on the line containing PQ? Can you find the distance of point R from line PQ? can you find the area of triangle PQR? And suppose we have another line containing PR, can you find the angle here? And suppose I have a vector PS, can you find the distance from S to the plane? Oh, I'm so sorry. You know, can you find actually the angle between the plane and vector PS? Okay, can you find the volume of this triangular pyramid? By just giving you 4 coordinates, then you need to answer those questions. Okay? So we are actually going there, not because I make it hard. No. Those are questions that you find even in your textbook. Okay? Now let me go on. You know what? It's 5:40 right now. Let me take a little break. We come back at 5:50. It seems like I'm coughing like crazy right now. Oops. The next part we will do is on the plane. So part B, planes. A plane can be determined by a point. A plane can be determined by a point and a factor normal to it, perpendicular to it. So suppose I have a plane. Let me use this. Suppose I have a plane. It doesn't have to be a nice plane. Let's make it like this. Okay, and we have a point on that plane called that point P naught. And this plane is normal to normal factor. Let's call that factor n. So this factor n here is normal to the plane. Okay, now we will find the equation of the plane by doing the following. Suppose I pick any random point on that plane, call that point P with factor with coordinate x, y, z, and we know one of the point contained in that plane is x naught, y naught, z naught. If I pick a factor from P naught to P, notice that this P is any point on the plane, a random point on the plane. Then factor P0, P1, this factor here must be x minus x naught, y minus y naught, z minus z naught. Okay, and however you choose that factor, because that factor is on the plane, notice that this the green factor must be perpendicular to the normal factor. See, right? Because the yellow factor is on the plane. You can try it yourself. Like you have table in front of you, okay, and then you draw any line on that plane, on that table. So this is your table. You draw any line. And then you choose any point on that line. You stick your pencil up perpendicularly. Notice that the angle between the point, between the normal factor and the line that you draw must be 90 degrees. Okay, however you draw the line, it must be 90 degrees. Okay, and actually that's where we get our equation. It is by having the dot product. Consequently, the dot product of P0, P1 and normal factor n must be 0. Okay. Furthermore, you will see that suppose my factor n is basically ABC. Okay, let's call this factor ABC. Then we will get x minus x naught, comma, y minus y naught, comma, c minus c naught. That's for factor P0, P1. Dot factor ABC, that will be 0. So a times x minus x naught plus b times y minus y naught plus c times z minus z naught, that's equal to 0. Notice that a, b, c later on will be given. X naught, y naught, c naught will be given. I can put them together. And the one with variables, I put them on the left-hand side in this case. Now the right-hand side, you see, you get, sorry, that one is incorrect. This is supposed to be a times x naught. Then it will get a times x naught plus b times y naught plus c times z naught, which is basically a constant. We will call that constant d. Okay, now we get the equation of a plane. Notice that if you have constant on the other side and the variable on the same side, then the coefficient of x, y, z represent the factor normal to the plane. Okay, let's see. For example, I do it next to it. For example, let's say plane P contains 2, -3, 4. That's my favorite coordinate for the day. And plane P perpendicular to the normal factor 4, 5, -2. Then the equation of the plane is given by 4 times x minus 2 minus 3 times x minus 5 plus, I'm sorry, wrong. The direction is 4, 5, -2, so this should be plus 5y plus 3. Oh, what happened? And then minus 2 z minus 4 equals to 0. But we usually don't leave it like this. We usually don't leave it like this. Multiply that out. And then move the constant to the other side. Okay, so this will be 4x minus 8 plus 5y plus 15 minus 2c plus 8 equals to 0. So we get 4x plus 5y plus minus 2z equals to negative 15. That's the equation. Okay. Now you may have another question. Suppose Thomas, how can I graph a plane on the three-dimensional space? It's kind of difficult. I know. Let's find out. Let's do another example. Example 2. Sketch the plane P given by, let's say, 2x plus 3y plus 4c equals to 12. What you can do is to find x and y and z intercepts. Okay, so find x-intercept. X-intercept, we know the y and c equals to 0, right? So you get 2x equals to 12, x equals to 6. Therefore, the x-intercept is 6, 0, 0. Likewise, for the y-intercept, the x and z equals to 0. I just do fast forward. Okay, so you will get y equals to 4, and the coordinates corresponds to that is 0, 4, 0. The c-intercept will be when x and y equals to 0, and the c equals to 3. Now, you can graph this already. Suppose this is x, y, z. The x-intercept is 6, 0, 0. The y-intercept is 0, 4, 0. And the z-intercept is 0, 0, 3. Okay, now this is the plane. Now, of course, the plane is not only the part in the first octant. It is extendable much further. Okay, but at least we can show you, I can show you the intersection here. Okay. Now, actually, from this example too, I want to teach you something else. Very interesting, something very interesting. I hope you appreciate this. You appreciate the beauty of the three, once you learn 3-dimension, you appreciate that, and you even can apply that to lower math courses. Okay, notice that if I use this guy here, I use this plane equation here, and I set the other side equals to 1, so 12 becomes 1. Of course, I divide by 12. I will get x over 6 plus y over 4 plus z over 3. Notice that the x-intercept, the y-intercept, the z-intercept. Okay? Why do I teach you this? Because there are questions in our textbook and also in my test later on in general. It's not only about my test though. The further you go into this course, there are things that you'll see so often, such that it's better for you to know how to do it super fast. Okay, but how if we reverse the situation? What if we reverse the situation? What I'm saying is, suppose I give you a sketch, or I give you 3 coordinates, x and y and z intercepts of a plane. A plane P has x-intercept 3, 0, 0, y-intercept 0, negative 2, 0, and z-intercept 0, 0, 1. Find the equation. Of course, you may think, oh, I need to graph that first. Actually, no, you don't need to graph that first. But if you want, you can. Okay, the x-intercepts 3, 0, 0. The y-intercept 0, negative 2, 0. And the c-intercept is 0, 0, 1. So the plane actually looks like that, right? Okay, of course, it's not just a triangle. It's extendable from that plane. But if you want to see the intersection to the basis planes, those are the ones, right? Okay. But can we find the equation fast? The answer is yes, we can. The equation is, use that technique, x over 3 plus y over negative 2 plus c over 1 equals to 1. And then multiply by the LCD, which is 6. Multiply by 6, multiply by 6, multiply by 6, multiply by 6. Done. You get the equation. Okay? Otherwise, you may need to do it in a very, very long way. Okay. Is this the only way to do it? This is the fastest I can tell you. Okay? But the way to find the equation is actually, if you look at our textbook may teach you different ways. Let's say, for example, I go back to that example 2, and suppose I have these intercepts here, 6, 0, 0, 0, 4, 0, and then 0, 0, 3. Okay, we know the equation already, 2x plus 3y plus 4c equals 12. Can I do it without using the technique I show you in example 3? In other words, can you do it textbook way? Yes, you can. Yes, you can. It's just harder, maybe. Okay, but bear with me. Bear with me. Let's call these coordinates coordinate P, Q, R, and I will call coordinate PQ. Factor PQ be factor A, maybe, which is negative 6, 4, 0. Okay, this is factor A here. Actually, let's not do it there. Let me copy paste that thing. So that you don't get confused. Okay, so we want to go backward now. Suppose example 4, suppose the x, y, z intercepts of a plane are given as in the figure. Find the equation of the plane. Now we know the equation already. This is basically the plane we have in example 2. We know the equation already. Okay, and if you do it fast way, you will get that equation really fast. Okay, basically you do it this way. Okay, this is the x, y, z intercept, and the other side here has to be 1. From there you multiply by the LCD. But suppose you don't do it that way. You want, some people just like it long, some people like it hard, right? How will you do that then? Then you make a factor PQ, which we call factor A. The components are negative 6, 4, 0. Well, because position factor for Q is 0 for 0. Position factor for the x-intercept is 6, 0, 0. When you subtract, you will get negative 6, 4, 0. That's how I get that. Okay, the way we did it before. And then let's use coordinate factor B here, from P to R. Okay, so PR is my factor B. That's negative 6, 0, 3. Okay, notice that the factor normal to the plane must be normal to PQ, must be normal to factor A, must be also normal to factor B. So I can set my normal factor to be A cross B. Right? Think about it. That's one of the factor normal to the plane, which is factor ijk, and then negative 6, 4, 0, negative 6, 0, 3. When I do the cross product, I mean that when I do the cross product, the first component is 12, the second component is 18, and then the third component is 24. Okay, notice that it has common factor. Let me use parallel. Factor n is parallel to that. Let factor n be the factor without the common factor, like the vector here without the common factor. So I will reduce by 6. That will give me 2 and 3 and 4. Okay, now from there, then we see, oh, you know what? Then the equation of the plane must be 2x plus 3y plus 4z. Do we have that up there? Right, 2x, 3y, 4z. Then Thomas, how do we get that 12? How do we get that 12? Plug in one of the coordinate. You can use coordinate P, you can use coordinate Q, you can use coordinate R. Either one of them will give you the 12. Okay, let's say I use coordinate R, 0, 0, 3. I will get 2 times 0 plus 3 times 0 plus 4 times 3, which is our D, so D equals to 12. So the equation is now complete. 2x plus 3y plus 4z equals to 12. Now compare that to my method. My method is, oh, I know the intersections. The x-intercept is 6. The y-intercept is 4. The c-intercept is 3. Set it equals to 1. Multiply by the LCD 12. So I get 2x plus 3y plus 4c equals to 12. Done. Okay. In other words, I get this because of, not only because I just do examples, I do exercise, right? But when you do an exercise, try to think a bit further, identify there could be some shortcuts. Okay. Remember, I think I said this to you on the first day of class. You may think that you are smart, but only smart people can get to calculus 3. Now, if our class is now full of smart people, and you, who is smart compared to your Calc 2 and Calc 1 students, classmates, in this class, maybe you're just average. Okay? Now, instead of thinking too high about yourself, try to practice and learn. And of course, it takes some humble heart to learn. Okay? When you pass this class, nobody ever asks you, say, do you study hard or not? Okay? And that's the same case for every classes though. If you got an A, that's an A regardless how hard you study. Okay? Nobody so proud that, you know what, I didn't study for that class even though I failed the class. Right? I mean, come on, man. What kind of a joke is that? Right? Okay. It's not about how hard you study or how easy you study. Give me a second. My daughter wants to play with me. Okay, so that's about the equation of a plane. Now let's go further. Some issues that we will need to deal with later on. For example, notes. Two planes are parallel if and only if the factors normal to them are parallel. You remember that two factors are normal. Two factors are parallel if one of them is scalar multiple of the other one. Right? Moreover, the intersection should be empty. In other words, they don't have any common points. In fact, if they already have parallel vectors, and they have common point, then there must be the same plane, identical plane. Okay, maybe I write it there. If the normal factors are parallel and the intersection is not empty, they have one common point, then the planes are actually the same, identical planes. They are not parallel. The word parallel actually implies that those two planes don't have anything in common. Okay, now of course, if you have parallel planes, one of our interests later on will be how do we find the distance between these two planes? Okay, which I think with the time I have right now, I think I will teach you that later on. Second, what happens if two planes are not parallel? The direct consequence of that is if two planes are not parallel, then they intersect at a line. Imagine if you have a plane intersect with another plane, the intersection must be that common line here. Just look at your textbook, right? You have page 1 and page 2. They may be two different planes, but they intersect at the spine. Okay? Now, the issue there will be, well, okay, if they intersect and give us a line, can we find that line? Okay, in fact, we can say further, if we have these two planes intersecting to the line, then what are the angle between these two planes? The angles between these two planes here. And you will see, this one is actually easy. The angles between these two planes is the angle between the two normal factors. Okay, if I move these factors to the spine, then you may be able to see that better. If I move these factors to the spine, okay, now you will see the angle we have among between the factors here is exactly the same to the angle between the planes. Okay, so that will be an easy question to answer. The harder one will be, for example, if I have a point not on a plane. If I have a plane and I have a point not on a plane, how do I find the distance between that point to that plane? Okay, and when we say the distance, it has to be perpendicular distance because that's the shortest distance. Okay. Now, let's work on the two intersecting plane first. Okay, so for example, I don't remember what example number, what is that? Number 5, I think. Example number 5. So we have plane 1 given by equation x plus y plus z equals to 1. Plane 2 given by x minus 2y plus 3z equals to 1. Okay, first question, find the angle. And part B, find the equation of the intercept of the line where P1 intersect P2 and P2 intersect. Okay, solution. Notice that P1 is normal to vector 1, 1, 1. Let's call this N1. And plane 2 is normal to 1, negative 2, 3, and call this N2. So part A, the angle between P1 and P2 is equal to the same angle between N1 and N2. Now, in 12.3, we have learned how to find the angle between two factors. That's why we always think of that from factors' point of view. Okay, so cosine theta equals to the dot product N1 dot N2 over the magnitude of N1 and N2, which is the dot product is 1 minus 2 plus 3 over the magnitude of N1 is square root of 3. The magnitude of N2 is square root of 14, which is equals to 2 over square root of 42. So our theta will be cosine inverse of 2 over square root of 42. From there, you use your calculator. 5 decimal places. Okay. Now that's just the routine calculator work. I don't finish it. How to find the equation of the line? Notice that when you pancake these equations, the equations of the planes, you notice that we have two equations, but more variables. In other words, we will have multiple points where they intersect. Like what I said earlier, it's a line. The intersection must be a line, right? So one way to work it out is to set one of the variables. You randomly choose one of the variable and call that, give it a number, the same number. Let's say, for example, I want to see, and this is just one way. It doesn't have to be like this all the time. Okay. Suppose L has XY plane intersect. The line L where these two planes intersect. Suppose L intersect XY plane. Okay. Then the intersection will be, the C has to be 0, right? That's the trick that we do, such that we now, instead of having two equations with 3 variables, now we have 2 equations with only 2 variables. Because we set we set the C equals to 0. Okay, then from here we solve it. For example, I think I would just use addition method. If I subtract this, I get 0, 3y, so the y equals to 0. Okay, now if the y equals to 0, then the x equals to 1. Is it right? In other words, line L contains 1, 0, 0. Happens to be a coordinate on x-axis, but it doesn't have to, because what we suppose is that that line intersect xy plane. Okay, so I set the z equals to 0. It turns out when I work it out, it intersects the x-axis at x-axis. But it doesn't have to be like this though. It doesn't have to be like this. Now, but once you get the line, the point on the line, then we actually get one ingredient of the line, right? Remember, for you to get a line, you need two things. You need to have the position factor. In this case is 1, 0, 0, right? The one we solve. The second thing we need is the factor parallel to it, the direction factor. Okay. How do we get that direction factor? This requires some thinking and visualization so that you can understand, oh, why we do it this way. Okay. Now take a look on this situation again. Notice that if two planes intersect, like the one I usually depict, let's say this is plane 1, and we have plane 2 intersect like this. Okay. What is the direction factor of this line L here? I strongly suggest you to follow me in graphing. Notice that the factor normal to P1 looks like this. Right? And the factor normal to P2 looks like this. And the phi, the direction factor we look for, the one that parallel to L, turns out to be, from that picture, you see that the direction factor that is parallel to line L, that direction factor is normal to the normal factor of plane 1 and also normal to normal factor of plane 2. Oh, therefore, if so, we can say that factor V must be parallel to the cross product. Remember this technique? So knowing how to do cross product is not everything. Okay, cross product is a tool for us to analyze a lot of other things, and one of them is here. Okay, so let's come back now. So what is the factor phi? Let factor phi be parallel to line L. We will choose V to be parallel to the normal factor, the product, not the cross product of normal factors. Okay, so V is parallel to I, J, K. By the way, you can just call that equal to. You can make it equal to, call that factor V to be equal to N1 cross N2. Let me just do so then. Okay, so this is 1, 1, 1, and then 1, negative 2, 3. So the cross product will be 5 plus 2, 3 plus 2 is 5, 3 minus 2 1 is 2, but the second component is opposite. Negative 2 minus 1 is negative 3. Okay, so at this point, we already see that line L contains 1, 0, 0. Notice I write it as a coordinate and is parallel to 5, negative 2, negative 3. Okay. Therefore, what is line L? Well, line L is given by RT equals to 1, 0, 0. This is the position factor of that coordinate 1, 0, 0. Plus T times 5, negative 2, negative 3. We can write it as 5T plus 1, negative 2T, negative 3T. That's the factor equation. How about if? So that's the factor equation. How about the symmetric equation? The symmetric equation will be x minus 1 over 5 equals to y minus 0 over negative 2 equals to c minus 0 over negative 3. Okay. Now, notice that I did the example 5, basically, if we have two non-parallel planes, we need to find the line, right? Then how do we show that two planes are actually parallel? We need to show these two. But to show these two, the first one is easy. In fact, that's the same work we did up there, how to show that two lines are parallel, right? Now, the next thing we need to do to show two planes are parallel, sorry, I scroll a lot. I need to show those two planes have no common coordinate. How do we argue that two planes has no common coordinates? Then you suppose they have common coordinate first. Suppose two planes intersect not in an empty set, then it must be, the intersection must be what? Must be a line, right? Now, if it intersect in a line, then you use this technique, the one I show you here, to find the line. And you will see there's no such line. Okay? You will see there's no such line if you have parallel planes. Okay? Let me give you an example. Let me just leave it there. How do I do that? Let me write it here. Suppose, for example, it's easy to actually to grab two parallel planes. Example 6. Let plane 1 be x plus y plus c equals to 1, and plane 2 be x plus y plus c equals to 3. Now you see that they don't have common points, because you see that this guy here and this guy here must be multiple of each other, right? In this case, if you subtract, you will get 0 equals to negative 2, which is a contradiction. So you get it directly that they don't have any common point. Okay. But Thomas, what happens if the coefficients are not the same, but they're still parallel? Then if they are not the same, then the coefficient the coefficient in plane 1 must be multiple of coefficient in plane 2. So let's say this is 2 and then 2 and then 2, for example, right? What can I do there, Thomas? Well, make them equal then. So I will multiply the first equation by 2, and I will get 2x plus 2y plus 2z equals to 2, 2x plus 2y plus 2z equals to 3. When I subtract, I still get 0 equals to -1, which is still a contradiction. Okay, so from here we see that n1, which is 1, 1, 1, n2 is 2, 2, 2. They are parallel. Okay, but P1 intersect P2 at empty set. So P1 is parallel to P2. That's on the easy side. Okay. Now, the next example I will work on is an example where we will derive a formula to find distance from a point to a plane. In this example, we will derive the formula. We can say a formula, but the formula we use for finding the distance between a point. Let's call that point P x1, y1, z1, and plane with equation ax plus by plus zz plus d equals 0. Let's try to picture this first. So I have a plane. Slant it a little bit. This is the plane. Ax plus by plus cz plus d equals to 0. And I have a point in space not on the plane. That's x1, y1, z1. Okay. Let me slow down a little bit. You are in calculus 3. Okay, so please do not expect that what you will see here will be a Mickey Mouse stuff. No. Okay, that will be discouraging though. If this is a Mickey Mouse, why do we need to call that calculus 3? It's just that easy. Okay, it will not be easy. At the same time, knowing that it will be tough should encourage you from this point of view. Okay, what you are doing here is something not everybody can do. That's first. And even if they can do it, they may not be willing to do it. Okay, so I encourage you to kind of like be patient a bit. Okay, now this is the situation. Let's start working on the work. From this plane here, notice that this plane is perpendicular to a factor A, B, C. Can you confirm that? Right? We will call this normal factor N. Okay. Now this normal factor n here is perpendicular to the plane, and of course I can play with this factor n here and make it right below that p. I turn that a little bit to the right. Okay, this n here is normal to the plane. Okay. Now I will choose a point on the plane. Any point is good. Any point is good. I will choose a point on the plane, call that P0 with coordinate x0, y0, z0. Okay, remember that coordinate is on the plane. So if I create a vector from the point on the plane to the point not on the plane, and I call that vector v maybe. Okay, let me tell the storyline here. Let x naught, y naught, z naught be element of the plane, and vector v will be call this what? Maybe p naught will be a factor from p naught to p. Now, of course, the factors component will be x1 minus x naught, y1 minus y naught, z1 minus z naught. Okay. Now, the distance d that we are looking for, is actually the component of factor v onto factor n. Think about it. You have this phi like this. You have the n looks like this. Right? What you need is actually the distance. Right? What you need is the projection. What you need is the length here, which is basically the component of v onto n. That's our d. Okay, so if I draw it like this here, okay, notice that if you see that green as a factor, the green factor is parallel to n. Okay, and that green factor is basically the projection of phi onto n. Now, since I just need the length, then we will talk about the component. Okay, so come back down here. The distance that we are looking for, d, the distance d that we are looking for is the absolute value of component of phi onto n. We use absolute value just to make sure that it doesn't become negative. Okay, but that's the absolute of n dot phi over magnitude of factor n. Okay, but magnitude of factor n must be positive. So I just need the absolute here. But what is n dot phi? N is a, b, c dot x1 minus x naught, y1 minus y naught, z1 minus z naught over the length of factor n. But if you see the length of factor n, the length of vector n here, that's square root of a squared plus b squared plus c squared, right? Long time no see. Now, then, if I do the algebra on the numerator, the denominators basically settle up already. That's square root of a squared plus b squared plus c squared. On the top, we'll have absolute of a times x1 minus x naught plus b times y1 minus y naught plus z times z1 minus z naught. Gada-bum, gada-boom. This is equals to absolute of a x1 plus by1 plus c z1 minus a times x naught plus b times y naught plus z times z naught. But we know earlier the equation of the plane is ax plus by plus cz plus d equals to 0. Okay, the plane, the equation of the plane is ax plus by plus zz plus d equals to 0. And because x naught, y naught, z naught is on the plane, then ax naught plus by naught plus zz naught plus d equals to 0. In other words, ax naught plus by naught plus zz naught equals to negative d, which I will replace there. This is the formula of the distance of a point from a plane. Okay, compare what we have on the top here with the equation of the plane. Notice that we basically replace the x, y, z from the equation of the plane by the coordinate not on the plane. Okay, so let's do some problem. I think the easiest problem we can get is for example 8, find the distance from of plane with equation 2x minus 3y plus 6c equals to 15 from origin 0, 0, 0. Then solution, the normal factor is 2, negative 3, 6, whose magnitude is square root of 2 squared plus negative 3 squared plus 6 squared. I believe that's 7. Notice that this is the denominator, right? The distance is equal to something over 7. On the top, I will use 2 times to, origin, 2 times 0. 2 times 0 minus 3 times 0 plus 6 times 0 minus 15. Well, because when I make this equals to 0, I get 2x minus 3y plus 6z minus 15 equals 0. Okay, so I get d equals to absolute of negative 15 over 7, which is 15 over 7, end of story, done. Okay, now we have 15 more minutes. Let me do more problems that is not covered in our textbook lecture. For example, suppose I have 2 parallel planes and we want to find the distance between these 2 parallel planes. Let P1 and P2 have this equation, 2x minus 3y plus 6z equals to 15. 2x minus 3y plus 6z equals to, let's say, 0. How do we find the distance between these two? Notice that each of these planes are parallel to this, is perpendicular to the same normal factor. Okay? And they don't have common points, because if you subtract, you get 0 equals to 15, which is a contradiction. Okay? So the issue is how to find the distance. Find the distance. The distance between P1 and P2. I'll give you ideas first. Think about 2 parallel planes. These planes are parallel, right? The distance between these 2 planes will be, we can find the distance between these 2 planes by doing the following. Let's call this plane 1 and this is plane 2. We can do it this way. Can you find a point on plane 1? Call that point Q. Okay. Then the distance between these 2 planes equals to the distance between point Q, which is in plane 2, and plane 1. Because however you choose a point on plane 2, the distance must be the same to plane 1. Remember, they're parallel, right? Now, notice that there are a lot of coordinates on point Q, on plane 2. Let's choose one of them. For example, you may want to find the x-intercept or y-intercept or z-intercept or any random coordinates that you can see fit into that plane. The one that we can fit here is origin. Notice that origin is in plane 2, right? Okay, so the distance between these 2 parallel planes is equals to the distance between origin to plane 1. But we have done that before, right? Okay, we have done that before. So you basically plug in origin into the equation of plane 1, 2 times 0 minus 3 times 0 plus 6 times 0 minus 15 over the magnitude of the normal factor of plane 1, 2 squared plus negative 3 squared plus 6 squared. That is 15 over 7, basically what we did in example 8. Believe it or not, we can actually simplify this computation even further because they have exactly the same equation here. Notice that 15 is basically the difference between these two numbers. Okay, as long as the coefficients you have for each planes are already the same. If not, then you need to do some adjustment first. Okay, let's do a little example. Suppose what we do instead is example 9b. Suppose our plane 1 is x plus 3y minus 5z equals to 7, and then negative 2x minus 6y plus 10z equals to negative 4. Notice that the normal factors for the first one is 1, 3, negative 5, and the normal factor for the second plane is parallel. Okay, so notice that n2 is negative 2 times n1. Okay, so n1 is parallel to n2. The plane may be parallel at this point, may be parallel, may be identical. How do we make sure that they are actually not identical? One way is you adjust one to be the other. Okay, so plane 1, the equation of plane 1 multiplied by negative 2. And plane 2, you say the same, set it the same. You'll get negative 2x minus 6y plus 10z equals to negative 14. Negative 2x minus 6y plus 10z equals to negative 4. So what is the distance between plane 1 and plane 2 then? Well, that will be the difference between those two, absolute of negative 14 minus negative 4 over square root of negative 2 squared plus negative 6 squared plus 10 squared. That will be 10 over 140, square root of 140. Okay, and anything from there, you simplify yourself. Now, further challenge. What happens if we have skewed line and we want to find the distance between those two? We have, not skewed lines. Skewed lines. We have that question earlier here in example 3. So let me steal that. And we do follow-up question from here. From example 3, instead we want to find it to show that they are skewed, we want to find distance between them. Find distance between L1 and L2. Now I have only 8 minutes remaining. I hope I can make it. The way we look at that will be as following. Suppose I have two planes, two parallel planes on which those two lines are located. So let's say So let's say those two lines are these lines here. One of them is this, and another one is this. Okay. So we already showed that those two lines are skewed, right? Now, how do we find the distance between them? Now, suppose this is our L1 and this is our L2. L1 is parallel to the direction factor 1, 3, -1, and L2 is parallel to direction factors 2, 1, 4. Notice that those two factors are on the planes, but they are coordinate free, right? So let's depict those factors. Let's say the phi1 looks like this, and then phi2 looks like this, which what I plan to do is I will find the factor normal to those two. Okay, take a look. If I copy this factor here and then move it down, okay, so this is our phi1, this is our phi2, this is also our phi2. Now, if I do the cross product will be perpendicular to the plane. Actually, the cross product will be perpendicular to both planes. Right? Yeah, because these two planes are parallel. Okay? Let's get that one first. So, solution. Factor n is normal to L1. Factor n is also normal to L2. Okay, so I can use this factor n and set it equals to phi1 cross phi2. One, 3, -1, 2, 1, 4. That will give me 12 minus -1, that's 13. 4 plus 2 is 6, that's -6. 1 minus 6 is -5. So this is the normal factor. Okay. Next, what I will do is I will find a factor between those two, between those two lines. So basically what I want you to do is choose a point. What color do I want to use? This one here. Choose a point on line 1 and a point on line 2. And create a factor from there. Okay. We will choose P1 in line 1 and P2 in line 2. Let's say the P1 be, we know that, right? One of the coordinate is 1, -2, 4. Is it right? And another coordinate in line 2 is 0, 3, -3. Is it right? Okay, so 1, -2, 4. Notice that these are actually given in the equation of the lines. So P2 is 0, 3, -3. So the vector P1, P2 will be -1, 5, -7. Now, notice that the distance that we are looking for, is equal to the absolute of the component of P1, P2 onto that normal factor. Okay, imagine this. Imagine if I copy this blue factor here and put it here. Okay, now the projection of that factor onto n will be, the component of that will be this thing here. The distance between those two planes. Okay. Let me just finish this up and then let you go. So this will be the dot product of n and P1, P2. So that's 13, -6, -5, dot, -1, 5, -7 in absolute, divided by the magnitude of n, factor n, but the magnitude of factor n is square root of 13 squared plus -6 squared plus -5 squared. Okay, you can continue your computation yourself. Suggested homework. From this 12.5, I would like you to do number 3 to 59. Okay, I kind of have a sense that a lot of you not done with your 12.4 yet. Please do. And I try to create the lecture videos from the supplemental videos for 12.4 and 12.5. You try to do that first. If you don't get it, then look at what I did. Okay, and then from here, after you're done with 59, then the following are something you need to think when you do these problems. The previous one, you still need to think, but not as hard as number 61 to number 79 are. Okay, if you are someone who say to yourself, I want to study and I want to go far in my academic career, you better do this. Okay, don't just say, oh, Thomas, you seems to be too hard, you seems to be demanding a lot. Trust me, once you transfer to UCLA, for example, I'm average. I don't want to say that I'm nothing too, but one of my job is to prepare you such that when you transfer to a school as good as UCLA, you can compete with students already there. Okay, this is where I stop. Remember, on Monday, we don't have class. See you then.
Professor.